Hello, Karthik, is it audible?
Yes, sir, it is audible, sir.
Okay, okay. So thank you. So good morning, one and all. So as per the schedule, today at 10 o'clock we are going to start the session. So please kindly wait for some time. అన్నయ్య గుడ్ మార్నింగ్. మైక్ ఆఫ్ లో ఉంది. అన్నయ్య మైక్ ఆఫ్ లో ఉంది. మైక్ ఆఫ్ లో ఉంది. హలో అన్నయ్య, ప్లీజ్ కమ్ టు అన్మ్యూట్.
సార్
అన్మ్యూట్.
చెప్పండి సార్, చెప్పండి సార్.
హలో తమ్ముడు.
నవ్ ఇట్ ఇస్ ఫైన్ అన్నయ్య. నవ్ ఇట్ ఇస్ ఫైన్.
Great, great, great. You can hear me, right?
Yeah. Now it is fine, Anaya. Right,
So,
okay.
great.
Thank you.
I'm sorry, I'm a bit late actually.
It's okay, Anaya. People are joining.
Okay, great.
So we'll start in after 5 to 6 minutes.
Yeah. తమ్ముడు
Naya?
so next talk is scheduled at 11, is it?
Yeah, next track is at 11. Yeah.
Okay, great.
Anaya, shall we share the screen so that is there any technical issue we can resolve?
Sure. Somebody is doing it, so please ask
Yeah,
them to
yeah,
stop it.
yeah, sure. I'll tell them.
Yeah. She has stopped it. Okay, I can do it now.
Right, Anaya. Yes, it's appearing. Fine.
Okay, so you can see, right?
Yeah, it's appearing.
Great.
Thank you.
So I think I leave it like this. It's okay.
Yeah, you can leave it like this.
Yeah. Do you really need my video, or is it okay?
Yeah, yes, we need it
Okay,
because even many participants used to ask, so we're doing for that.
fine.
Anyway, it is YouTube live also. We'll try to. It is available in the YouTube, so we can edit also later.
No, that's fine. So what I'm saying is that okay, in the case that the bandwidth is not enough, right? Then I will stop it. Okay.
Okay, right, fine.
It depends on the internet speed, actually. Yeah.
Sure. Anil.
So we'll do it. No worries.
Yes.
So give me a minute. I'll just take water and come back.
Okay, Anil. Sure.
తమ్ముడు
Yes, Anil.
Okay, so is that in this audience, right? Do you have some BTech students as well?
Yes. Final year BTech students are also there.
Great. Okay.
Final year BTech students and MTech students and also research scholars.
Okay, great. But
And
anyone from RGKT?
yes, from RGKT also.
Okay, great.
RGKT from MME, I mean Material Science and
Yeah,
Metallurgical
material science,
Engineering,
metallurgical engineering, I know.
and also some students from electronics background and EC and chemical engineering students also there.
Okay, so I'll try to talk in such a way that interdisciplinary.
Yeah, sure.
Yeah.
Even the faculty also from different areas of
Okay.
which
But
covers
my
this.
topic, honestly, it is directed to students.
Yes, okay, fine.
Yeah.
So, Bhavani madam?
Sir, shall I start?
Yes, madam, please.
Okay. Hello, good morning, and welcome to all the delegates, all the participants, all the speakers, and our colleagues to our international webinar in synthesis and characterization of nanoparticles and its novel applications. Today is the third day, and I hope that all of you are interested in this seminar. So continue for one o'clock for this last day, and we hope that this seminar will be very helpful for you. So I hand over the speech to Bhaskar sir so that he introduce the one speaker, today talk speaker.
Thank you, madam. Thank you. So, good morning, participants. So, myself, Bhaskaraya, Assistant Professor, Department of Physics, RQKT, RK Valley. Now, I would like to introduce our today's speaker, and we have a 12 years of interaction with him as a brother and as a friend. So, Dr. Chandrasekhar Murapaka. Right now, he is an assistant professor at Indian Institute of Technology, Department of Metal Science and Metallurgical Engineering, IIT Hyderabad. So, his education background, he has completed his MSc Physics from Andhra University, Visakhapatnam in 2006, and he has completed his MTech Solid State Materials from IIT Delhi in 2009, and he has completed his PhD from Nanyang Technical University Singapore in 2014, and he has received many awards at the national and international level at IEEE, and he is a DST Inspire Faculty Fellow in 2017, and he's having a list of publications, 32 international level, and also 4 patents. Among 4, 3 are US patents, and he's having many projects like DST's SAB, and his area of research is spintronics based memory and logic devices, nanomagnetic materials, domain walls, and micro nano fabrication techniques, etc. And his professional experience before joining to IIT Hyderabad, he has worked as a research associate at Nanyang Technical University Singapore from 2014 to 15, and from 2015 to 16 he worked as a he worked as a science senior engineer at technology development and research engineer at Spintech France, and also research fellow from 2018 till he is joining to IIT Hyderabad at Nanyang Technical University. So with this brief introduction, I would like to invite our speaker, Dr. Chandrasekhar Murapaka, to deliver his speech. Over to you, Dr. Chandrasekhar Murapaka.
Okay, thank you, Bhaskar. Yeah. So
Thank you.
yeah, so good morning, everyone. So first of all, I would like to thank Bhaskaraya for giving me this opportunity to present today some of my work on spintronics for memory, logic, microwave, and biomedical applications. So I would like to give you a flavor of what is spintronics and what is the basis of spintronics, basically how the ferromagnetic materials can be used in spintronic application. Then I will talk about few applications. I won't bother too much. So this talk I targeted mainly to the students. Okay, so I'm really pleased to give this talk today at RGKT because many of my friends are working at RGKT, and as Bhaskar mentioned that I shouldn't even mention that he is my friend. Actually, he's my brother only. We have a long association of 12 years from IIT Delhi, and many of my other friends like Ganesh, Prabhakar, Srinu, they are all working at different RGKTs. I think they are at Newsweek. And one of my close friend and guru, Venkaya, so Venkana Garu, he was working at Newsweek. So I'm really happy to give a talk at RGKT. Okay. So before I start my presentation, I must thank many people who have helped me in this way towards learning a lot of things in research. So my PhD I have completed at Nanyang Technological University, where I got many friends and who have assisted me in conducting the research. And especially I would like to thank my guru, Professor Liu Wenxian. And at Spintech, I have done my postdoc for 2 years, and where Dr. Ursula Abels, she was my supervisor. And I would like to also thank now not only my gurus, but my students also now. At IIT Hyderabad, I have 3 students, Manoj, Sriram, and Vivek. And I would like to make you all a note that this first student, Manoj Talluri, he is an RGKT student from RGKT Newsweed. Okay. And he's doing very well. So he's your kind of elder brother who is doing very well to just, I'm telling you this to inspire you. Not only Manoj and many of other friend, many of other seniors of yours are doing very well at IIT Hyderabad as PhD student, and each and every recruitment at least we get 1 or 2 very good students. Okay, so it is just to inspire you that you people are doing well. And I would like to thank also DST SCRB for funding for the Early Career Research Award to conduct this research. Okay. However, I would like to give a small note here that whatever I'm presenting today is mostly done at NTU and Spintech. Okay. So without delay, I would like to, the basis for spintronics are the magnetic materials. So like I think you know that the basis for microelectronics is the semiconducting materials, like a silicon, it's a God material, we all know that. Okay, so you can easily make it P-type and type. Similar to that, if you want to work in spintronics, we should understand a little bit of magnetic materials, especially ferromagnetic materials. Okay, the fun part is that okay, we all have played with magnetic materials from our childhood. So we take a pin and then we bring close to a magnet, or we have this fridge magnets, refrigerator magnets. We have played with it. So magnets are not a foreign elements to us. Okay, and just want to let you know that Earth itself is a magnet. So we are standing on a magnet. Okay, so magnetic materials are nothing. Okay, if silicon you say that is an abundant material, we are standing on a magnetic material itself. Okay, with a north and south. So the only difference is the magnitude. Okay, so if you see that what is the magnetic field of Earth, it is around 50 micro Tesla, so which is very small. Okay, you cannot say that is small because our human brain itself has magnetic fields due to the small currents that are flowing in the neurons. And then what is the magnetic field that is coming because of it? It is around 1 femto Tesla. So as compared to femto Tesla, you know, micro Tesla is much better. Excuse me. My sincere apologies. Okay. So I would like to give a brief history of magnetic materials. Okay, so even before we call them magnetic materials, Greeks already found before Christ. Okay, even in 800 BC, we found Greeks found this magnetic materials where they found a lodestone which is attracting the ferromagnetic elements like iron ore and all these things. Okay, but it was a lodestone which is a ferromagnetic material, and we all know that all this globalization has started because of the marine compass that is found, that you can find which direction is north, which direction is south. So due to this, Europeans could voyage onto the sea, and then they could explore the world. So the globalization, the first step started from a magnetic material, that is the marine compass. Okay, that was invented in 1200 AD. Before that, people were staying where they are. Okay. So what is the origin of magnetism in materials? Okay, so honestly, I want to tell you that, so origin of magnetism, right, it is just like origin of electric field. Okay, so we know that there are 2 fields. Okay, one is electric field, second one is magnetic field. And we all know that the origin of electric field is charge. Okay, so now we will know that what is the origin of magnetic field. Okay. So I think we all have seen such kind of experiment when we are in childhood, that you just take a copper coil. You know that copper is a non-magnetic material, but you attach it to, you make it a coil and then attach it to a battery. What is going to happen? It will just act like a magnet. It can attract the small pins. So now I think I made it clear that, so the electric field is coming from the charge, whereas the magnetic field is coming from the current actually. Okay, so the origin of magnetic field is the current. So basically both are coming from electrons. So static electrons are giving the electric field, whereas the dynamic or the moving electrons are giving you the magnetic field. Both are, the origin is same. So I think we should remember Ampere for this, because even before the electrons were discovered, I think electrons were discovered around 1900s, but even before the electrons were discovered, this guy said that the magnetism could be because of the some molecular current. So see, he could have that intuition to tell that, okay, what is the origin of the magnetic field? Okay, and we should kind of give the credit to him to unify the two different fields. So one is the electricity, second one is the magnetism. He unified these two and then have come up with the electromagnetic theory. So we all have been studying all this. Okay, but now the question is, if you take iron, okay, a simple iron, small rod, and then you rub it with a magnet, right, with a permanent magnet. After that, it can act also as a magnet. But now my question is that where is the current involved in this? Okay, in this case, I know that, okay, there is current involved because of the current that is flowing. So you have applied some potential from the battery, right? Whereas in this case, when I rub a magnet with another iron with another magnet, why is it becoming magnetic? And why, in the first place, a permanent magnet has a magnetic moment when there is no current flow through this? So whenever we have a property to be explained, what we need to do, we need to immediately go to their atoms and see there how the behavior of the atoms can affect the properties. So I think you all have seen an atom, okay, not seen, but at least could visualize an atom, where you can see that this is the nucleus where electrons are orbiting around the nucleus. So just like Earth is orbiting around the sun, there is a lot of symmetry here. Okay, so we are standing on Earth, which is orbiting around sun, right? And then we are made of atoms where electrons are orbiting around nucleus. Okay, so coming back to the story, now where is the magnetic moment coming from? So if you can clearly see that these electrons are never staying, they are never staying still, they are always rotating. So whenever the electron is orbiting around nucleus, you can see that electron motion can cause some current. Okay, so I can call that current as orbital current, obviously, right? So electron is moving in orbital motion, so that is orbital current. So whenever electron has a current, it can create a magnetic moment. So atom can have magnetic moment, but it is not the complete story, because electron, we know that it is not only orbiting around the nucleus, but it is revolving around its own axis. That is what we call spin. So just like Earth is orbiting around the sun, right? But it is also having a spin. So similar to that, electron also has a spin. So whenever electron is spinning, it can create another which can also give the magnetic moment. So if at all you people have heard about LS coupling, L is the orbital moment and S is the spin moment. So this LS coupling, okay, that spin orbit coupling is the origin of the magnetic moment. So I have already explained two currents that are present in the atom. So I think I convinced that atom can act as a magnetic as a magnet because of the magnetic moment. But okay, on a light note, I also want to tell you that you must be thinking that nucleus is also spinning just like sun is spinning, right, on its own axis. Yes, it is true. So nucleus can also give the magnetic moment, but the only difference is that electron mass, right, is around 10 to the power of minus 31 kg, whereas the nuclear mass, because of the heavy particles like neutrons and protons, it is 10 to the power of minus 27. So it is, I think, 3 orders difference is there. Okay, so when the magnetic, you can see the Bohr magnetron, that magnetic moment coming from the orbital motion of the electron or the spin motion of the electron is EH by 4 pi m. So when you take the m, so mass of electron is small, so that you can get a more magnetic moment. But whenever you take mass of the mass of the nucleus here, which is 3 orders high, so the magnetic moment coming from the nuclear current, right, the spin current of the nucleus is very small. Okay, so I think I just gave you an idea, even though I think you might know it already, but how the 3 different currents are there. Okay, so electron has an orbital current, electron has a spin current, and finally the nucleus has a spin current, and all 3 can give you the magnetic moment. They all can contribute to the magnetism in the materials. Okay, if that is the case, right, every atom can be a magnet, right? Because every atom has 3 different currents. So that is true. But then you can ask me question that why we have different class of magnetic materials. Okay, I think you all heard of different materials like diamagnetic material, paramagnetic material, ferromagnetic, antiferromagnetic, ferromagnetic. So where the difference comes from? Yes, there is a lot of difference come from how the electrons are arranged within the atoms, how they are filled in the orbital shells. So the electron configuration of the atom, and also that how they interact with each other, that is the exchange interaction between these atoms inside the material, can give you various types of materials. That is ranging from diamagnetic material to ferromagnetic material. So first of all, we discuss about diamagnetic material. So basically, diamagnetic material doesn't have any magnetic moment. The reason being is, that diamagnetic materials have completely filled shells. So every electron, let's say that it is having one spin plus half in one direction, there is minus half that is next to it. Okay, so one is spinning in clockwise, the other one is spinning in the anti-clockwise direction. They cancel each other. So when the currents are cancelled, the magnetic moment that is coming from the diamagnetic material is cancelled. So when the completely filled shells are there, each electron is going to cancel the magnetic moment coming from its next electron. So that is the reason that you don't have any magnetic moment. However, when you apply an external magnetic field, yes, diamagnetic materials try to uh, induce some magnetic moment in them. So it is, I think you might have heard of Lenz's law, where so the magnetic flux, right, is going to create an external. It is going to create some currents whenever you apply an external magnetic field. It will create a electric current in such a way that the magnetic field will be opposed. So the magnetic field created by the current is going to be in opposite direction. It is just like a son is going to oppose his father. Okay, so the reason is that these currents are induced because of the external magnetic field, but their movement or their direction in such a way that it opposes the source. So that is the Lenz's law, and it exactly works in the diamagnetic material. Of course, it has very good application. So because of this, right, whenever you apply a magnetic field, it will oppose it. It will try to expel the magnetic flux out of it. Okay, so if at all we can create a perfect diamagnetic material, we can create magnetic levitation. Okay, and we all know that superconductor is a perfect diamagnet, so it expels all the field lines. So the moment you apply a magnetic field, it is going to expel all the moments, and then it will levitate the material. So where can it be useful? It can be useful in the magnetic lev trains. So you can see that you can drive a train not on the track, but just above the track. There. Okay, so you can have this magnetic the train not just going on the track, but it is going just slightly above the track because of the this magnetic levitation, so that you can defy the friction. So you can get a very high speed. You can go even to you can see up to 600 kilometers per hour, which is more than the speed of a sound, and also you can reduce the power required to move this kind of drive these trains. Okay, this is all about diamagnetic material. Now we come back to the intrinsic magnetic moment. So I have just explained you that if you have an atom where all the orbitals are filled, okay, then you will have diamagnet. So what if you have one unpaired electron? Then you will have that unpaired electron is not going to be compensated by any of the other electrons, because it is unpaired electron. So if you have two electrons like this, they are going to compensate. You will get a zero intrinsic moment, right? Whereas only one electron is there, which is not paired, so you will have an intrinsic magnetic moment. Okay, so such kind of intrinsic magnetic moment is responsible for the all other types of magnetic materials, like paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic materials. Now, what is the difference between all of them is the interaction, how they interact with each other. Each magnetic moment is interacting with its next magnetic moment. Okay, so you can see here in a paramagnetic material, it is just like you have this unpaired electrons. Okay, just like aluminum, you have unpaired electrons that is creating the magnetic moment, but they don't interact with each other. However, whenever you apply higher magnetic field, the moment you apply magnetic field, all these fields will come to in a particular direction along the external magnetic field. The moment you remove the magnetic field, it will just come back to the same situation. Okay. So this is all about the paramagnetic material. So what if we can have a higher exchange interaction? What if we have kind of helping each other to keep all of these magnetic moments together? So that is strong exchange interaction that can create the ferromagnetic material. So this ferromagnetic material can create this spontaneous magnetization even if you remove the magnetic field. So you can saturate these magnetic moments in a particular direction. So when you remove the magnetic field, still there will be some remnant magnetization that is left. So the only difference between paramagnetic material and ferromagnetic material is the exchange interaction. Okay, so these ferromagnetic materials, which I'm going to talk a lot about today. And finally, we have antiferromagnetic materials, which this exchange interaction here is positive, that they are all aligned in one direction. Whereas this in antiferromagnetic material, they are all aligned in opposite to each other. Okay, so the exchange integral is negative, fine, as compared to the positive here. And in ferromagnetic materials, they are again like antiferromagnetic materials, where these spins are opposite to each other, but the magnitude is different. Okay, they have a different magnitudes. So what are the applications of ferromagnetic material? Today, in this talk, I will only focus on the ferromagnetic materials, not on the other magnetic materials. We know that we have been using hard disk drives to store the data, and you can know that these ferromagnetic materials can create a lot of magnetic field to do the magnetic MRI imaging, and also you know that I'm extremely sorry that I'm at home and a lot of disturbance is there. Okay, so you know that to convert energy between mechanical energy to the electrical energy and vice versa, you need magnetic fields. We know that, right? Like Fleming had left hands rule. You can change the mechanical motion, so mechanical energy into the electrical energy, and also the opposite. And also these ferromagnetic materials, right? They also have the applications in uh, uh, cancer therapy. I will explain you in detail when we come to that part. Okay. So in this talk, I think I form a basis of what are these materials first of all before I go to the applications. So now I'm going to talk about the applications of these ferromagnetic materials in basically in three different. So let's say that you take a photo. So what are you going to do first? If you like it, you save it. So first of all, I'm going to talk about how to store the data. So that is the data storage. Okay, if you don't like the photo, what you can do is that before you delete it, you can just do some cosmetics. You can do some processing on that. So that is called computation. So I'm going to talk about how to compute the data. And finally, if at all you like the data and you have done enough cosmetics on that photo, right? What you will do, you will share with your friends in WhatsApp or Facebook, whatever. So then you will have to have communication. So in this talk, I will explain you how ferromagnetic materials can be helpful according to spintronics to do data storage, okay, and data processing and data transfer. That is the wireless communication. And a small note that I will also talk about how these ferromagnetic materials can also be used in biomedical applications. So basically this talk is like an interdisciplinary, because I know that the students are from various backgrounds. So I try to keep it as fundamental as possible, so you can ask any questions later. And finally, I will conclude it. So, what language a computer can understand? So we all can speak Telugu, English, Hindi, Russian, Spanish. But computer, whatever the language you speak, it can understand only two digits, 1 and 0. This is the binary. And in conventional microelectronics, like you can see a laptop or a phone, right? So what is the heart of this? And who is processing these ones and zeros? Okay, that is a microprocessor, which is at the heart. Okay, and which is made of billions of transistors. So the building blocks are the transistors. So how this 1 and 0 are represented in microelectronic technology? Okay, so it is represented by the charge flow. Whenever there is a charge flow, it is a field effect transistor where there is a source and drain, and depending on the gate voltage, you can create a channel or you can annihilate the channel. So whenever the channel is created, so it is just like opening the dam gate. So whenever you open the gate, the water will flow. Okay, whenever you close the gate, the water won't flow. It is as simple as that. Okay, so whenever the gate voltage is applied in such a way that the channel is opened, you can flow current through this transistor. So then the charge flow, the current through this, the presence of charge at the channel can be represented by 1, and then the absence of the charge can be represented as 0. So today what I'm talking is that I'm going to give you a new convention, okay, how to represent this binary bits 1 and 0 in spintronics. Okay. And we all know that I'm not going to bring any other particles to represent this spintronics. I'll use still electrons only. Okay, so in microelectronic industry also we are using electron only, but we are using the charge property of the electron. Okay, so you know that okay, electron charge can only be negative. Okay, it can never become positive. We know that. The reason being is that electron is, I think I read a joke, let me tell you. So electron is always maintaining social distance from the positively charged nucleus. So it will always stay negative. Okay, so we should always maintain social distance to stay negative. Okay, anyway, jokes apart, what I want to say is that electron can never become positive. It is just staying negative. Okay, however, electron has another property, not only the charge, but it has a spin property. So electron spin, you can see that can be clockwise or anti-clockwise. So in simple terms, what I'm saying is that electron can have a magnetic moment in plus half direction. Let's say if it is the clockwise direction, and if it is a anti-clockwise direction, it can have minus half spin. So this plus half spin, that is the up spin, can be represented as 1, and minus half spin can be represented as 0. So I'm not using the charge property to represent the binary bits 1 and 0. Rather, I'm using the spin property where the electron can have two spins, okay, 1 and 0. Okay, so from now on, I'm going to talk about only the spin property of the electron to represent the up spin and down spin to represent to do the data storage, data processing, and the data communication. Okay. And what are the advantages? Of course, the first and foremost advantage of spintronics is the non-volatility. So what is non-volatility is that, okay, let's say if I take a charge-based device like a capacitor and you keep it aside, okay, so after 10 days you come back, right, the capacitor is completely discharged. But I give you a magnet, I have magnetized in north-south direction in a particular direction, okay, and I kept it at the corner of a house, and then I came back after 10 years. You know that the magnet still stay as the magnet. The reason being is that the spin, right, will always stay irrespective of whether you're powering up or not. You don't need to refresh the spin of a spin or the magnetization of a material. Okay, whereas the charge, you always have to refresh it. And moreover, the spin switching is faster than the charge transfer because spin switching doesn't require any physical motion. Charge transfer, electron has to flow from the source to drain, whereas the spin, it just need to, magnetization has to just go from up to down. So the spin switching is faster than the charge transfer, and the power required is also relatively low. Okay, and also it has a radiation hardness that, let's say that you are going to send a spacecraft into the space, right? Okay, the satellite into the space, where you just need to integrate some this memory and computation things, right? You cannot always use charge-based devices because you know that space is completely filled with plasma, okay, and many charge particles are always bombarding. So whenever there is a charge particle, it will create an electric field that can manipulate the data stored in the microelectronic data storage. Whereas the spin, the electric field that is coming from these charge particles cannot affect the spin direction. So spin-based devices have the additional advantage as the radiation hardness. Okay, I think this is very much true that we all take photos for our memory. So what we do once we take a kind of a selfie, immediately we want to upload in somewhere, Twitter, Facebook, Instagram, whatever. So where do you think that this data is being stored? So when you're uploading an image into WhatsApp, he has to store this data, right? Because you are sharing from your phone to somebody else's phone. Okay, you are sharing a photo. So where does this data store? And also, how much data each day we are creating? Now we have a lot of everybody has a smartphone, everybody has a laptop, and all these things, right? And we have been creating a lot of data. You know how much of data we are creating each day? That is 2 quintillion bytes. Okay. So this is 2 quintillion bytes. I think there are several zeros, I think. Okay. So this much of data we are creating each day. So where is this data going? Where is this data being stored? Okay. If at all you want to store, like I think we all have seen a CD, right? A compact disc, like where we used to watch movies in a CD drive, right? Earlier, maybe 15 years ago. Okay. So if you want to store this much of data in a compact disc, right? So within 1 second, just you need 1 second. If you stack them one on top, right, you can go from Earth to Moon. So that many CDs are required. You don't even need to create a spacecraft for Chandrayaan. You just keep on stacking these CDs, you can go to Moon. Okay. So jokes apart. we know that, okay, this data is being stored in cloud storage. So what is cloud storage? Cloud storage doesn't mean that, okay, we are storing data in somewhere in cloud or Mars or moon. Actually, cloud storage is nothing but it is being stored at a data center somewhere in US or Singapore, Germany, somewhere. Okay, so you will have a place where you stack so many hard disk drives. Okay, so you need to keep a lot of hard disk drives to keep this data flowing back and forth. Okay, so how this to make an efficient data center, what is required? Okay, so the required thing is that you need to keep this data size as small as possible. So you need to store the data inside this data storage center, right, in the data storage element with a small space. So the storage space that we are using for each and every byte should be as small as possible. Then only we can store a lot of data. So what we need to do is that we need to increase the density. Okay, so for that, what we have done in spintronics, right? So we have used this magnetic state. So the magnetic state of a material, if it all, let's say that this is 1 and this is 0. Okay, so the minus x, or as you can see in my hand, right? This is 1 and this is 0. So how do you read this? I can just say that, okay, I can store the data like 1 and 0, but how to read the spin state? So that is simple. What you need to do is that you need to keep a reference. So let's say this is the magnetic layer, okay, in which the spin is in this direction, and you have another magnetic layer where the spin is in the same direction. When you flow a small current through this, okay, then what is going to happen is that you can see that majority electrons are not going through any scattering, whereas the minority electrons are going to get scattered when they're parallel to each other. So what happens when they are anti-parallel to each other? You can see that now the magnetic moment of the top layer is anti-parallel to the bottom layer. You can see both majority spin and minority spin, both are getting scattered at the interfaces. In this case, only one electron is getting scattered, whereas in the other case, both electrons are getting scattered. So what is going to happen? For the anti-parallel case, you will have a high resistance because of the high scattering at the interface, whereas parallel case, due to the relatively small scattering, the resistance is going to be small. So just by measuring, just you apply a small bias current and measuring the, just by measuring the voltage drop or the resistance across the junction, you can tell that which kind of spin is there. Okay, I'm not telling something that is being invented here now. It is invented somewhere in 1988 and 89. Okay, so by Albert Fett and Peter Grunberg, this phenomena is called giant magnetoresistance phenomena that comes from the spin-dependent scattering. Depending on the spin, the scattering is happening. So now I have clearly told you how to read a spin state, but how to manipulate a spin state, because it's not only that you read it, but you will, whenever you want to switch it, you will have to switch it, right? It's not like we always need, let's say I'm bored with watching one movie, I can just clear this movie and I should be able to store a new movie, right? So you will have to erase it and then write with a new movie. So how to write a spin state? So for that writing the spin state, we need to use the spin transfer torque, where you have a polarizer, same stack. You can see that you have two layers. This is one ferromagnetic layer, this is second ferromagnetic layer. So when you flow electrons through it, right, you can see they are anti-parallel to each other, the polarizer and free layer. When you flow electrons, so when you apply current in such a way that when the conduction electrons are flowing through the polarizer, so due to the spin-dependent polarization, so these electrons will get polarized, just like you know that light gets polarized, okay, by a polarizer. So you can see that the electrons that have random spins here got polarized, and when they are flowing through the free layer, they can exert the torque. You know why? Because they have their spins away from the spin direction of the free layer. So when they are moving through this free layer, they will have to again change their magnetization direction, their spin direction, right? So when the electrons are changing their spin direction, so they will have to change their angular momentum. So when they are changing their angular momentum, so they will have to conserve the total angular momentum, they will exert some torque to switch the magnetization. So what I'm telling is that you don't need to understand everything, but just I want to tell you that I can use a small current to read the spin state. I can use a large current to switch the spin state. So basically what I'm doing is electrical manipulation only. A small bias current can read it, a large current can switch the magnetization back and forth. So now I have clearly given you an idea that how can we read a spin state and how can we switch a spin state. course, we should always remember the people who have contributed to such great phenomena where we are following in this research in spintronics. So for the discovery of this giant magnetoresistance for reading the spin state, right, the spin dependent scattering, Prize has been awarded to Albert Fert and Peter Grunberg. Okay, and these are the Nobel laureates. And for predicting the spin transfer torque, Luc Berger and J.C. Slonjewski, they were awarded this Olivier Buckley Condensed Matter Physics Award in 2013. So how the spintronics revolutionized the data storage? I would just like to give you an example. So if you see the first hard disk, I think you all have seen a hard disk. I have no doubt that any one of you can say that I haven't seen a hard disk. You all have seen a hard disk, right? And this is the first hard disk, okay, made in 1956 by IBM. Okay, you can see that there is a lift. Okay, the crane is being used to lift this hard disk drive to load into the helicopter. Okay, then just want to let you know what is the data storage density and what is the price and also the size. So the data that you can store in the first hard disk drive is only 5 MB, 5 megabytes. Okay, and the weight is 1 ton and it costs $50,000. Okay, in 1956 it cost $50,000. Fine, and now you can imagine how much it would be. And with the revolution that has brought by spintronics with these two phenomena, that is GMR, giant magnetoresistance, and also the spin transfer torque. Okay, basically the hard disk drive levies basically fundamentally on the GMR phenomena. Now we have a hard disk drive. You all have one, or you have seen one. So this is the hard disk drive that is in our hand, which can store few terabytes. So what is the difference between them? Just for fun, I'm telling you. With 5 megabytes, you can store only one audio song with this much of bulky thing. Whereas in, let's say if it is a 2 terabyte, you can store at least 1,000 movies, 1,000 HD movies in this hard disk drive. Fine. So you can never watch all of them. If you continuously watch, you need 2 years. Okay. So that much of difference has done. So the density has increased by 1 million times because of the revolution that has brought by the spintronics for the magnetic data storage. Why I'm saying all these things? If everything is done right, what is the point to do still to continue to do research in this area? Of course, there are always some areas that will that needs improvement and then new innovations and discoveries. Okay, so now I'll come to the first part of it, that is data storage. So just now I mentioned that okay, hard disk drive is very good. It can store a lot of data. It can, and then we know the price is maybe I think few thousand rupees. So if everything is fine, that why we still need to work on spintronic based memory? The reason is the hard disk drive is an external hard drive, so you can just store data externally. Okay, but you cannot use this data close to the computational algorithm logic unit. So if you take the memory architecture of a computer, right? This is the current memory architecture. You have a CPU where all the processing is happening. And you know that the processing happening very fast. Okay. To help the processing to happen very fast, you need to have the data storage device, which should work also with the similar speed or even higher speed. Okay. So that's why we have a static RAM and a dynamic RAM. So static RAM, random access memory, is going to give you the data back and forth. So it will give the input data to the processing, and then it will take the data and then give it to the dynamic RAM. But why this static RAM and dynamic RAM are still volatile memories, still charge-based memories only. The reason being is that if you know that hard disk drive, right, whenever I think you make it on, right, you will hear a sound. You know why the sound comes? Because there is a rotation, there is a physical rotation that is happening of the disk. So whenever there is a physical motion that is there, right, so the speed of the device is going to be smaller. Okay, so we need to come up with solid state drive where there is no physical motion. Okay, so what is our aim or objective right now is to replace the static RAM and dynamic RAM, which are volatile memories, with non-volatile spintronic memories. So if we can come up with a high speed magnetic memories, hard disk drive is good. It can store very high data, and then it is very high density, very bulky, and with the cost is also small. However, the speed Okay, whenever we buy something, right, we all know this thing. So whenever we buy a device, what we want it should be high speed. Okay, and then it should consume low power. So our power consumption should be low, so that, okay, let's say I buy a phone. Let me tell you. So I buy a phone. What I want to look for is, first thing is that the speed is faster. Okay, high speed. Second, power consumption should be lower, so the battery should come for at least 2 to 3 days. I'm just saying. Okay. Third thing, the price should be as small as possible. Three things. And fourth thing, it should be as compact as possible, as small as possible. So whenever you are making a device, okay, for an application, right, you need to think of four things. Okay, high speed, low power consumption, and then compact, as small as possible. Finally, you need to get all these things with a very small price. So hard disk drive is qualifying some of these things, which is what no, power consumption is also higher, high density, compact. Okay, and then it is compact and it can store a lot of data, but the power consumption is higher for hard disk drive. The second thing is that the speed is very small. Okay, so due to this, hard disk drive cannot be used as a memory, as a random access memory. It can be used only as a standalone memory. So now we have to come up with a non-volatile spintronic memory, so that we can get rid of the volatile memories. So why I'm saying that we have to get rid of the volatile memories? The reason is that, if you remember, I mean, if you all have seen, right? So you charge your laptop and keep it off, right? And then after 10 days you come, right? Again, you have to charge it. You may wonder that you have charged it fully charged, but you didn't use it at all. But after 10 days, why? The battery is draining, or your power, right? Your PC, right? Even though you shut it down, right, still you need to refresh the random access memory. So RAM always need the refreshing of the power, of the refreshment with the power. So whenever you are refreshing the RAM, right, that can cause two things. One is that you are having this quiescent power, the standby power, which is not at all necessary. You are not doing any processing, but still you are keep on adding the power. It is just like that. You are filling a bucket, but which has a hole. So the bucket is just leaking. Okay, and then you just keep on filling which is of no use. And second thing, whenever you are continuously applying the power, the heating issues will be there. I think we all see that you use your laptop for 2 hours, and then you put your hand on the laptop, you know that it is getting heated. The reason being is that it is the charge base. So whenever there is a charge flow, there is a joule heating that is involved in there. So whenever there is a joule heating, and then your devices are getting heated up. And same is true with your phone. You talk for a half an hour or 1 hour, you can see that not only phone, even your ear can get heated. Okay, so be careful with it. So our aim right now is to replace these charge-based devices with the spin-based device. So with that, I would like to show you that one such kind of solid-state device where there is no physical motion of the track is required. We have made such kind of thing during my PhD. So we have used this domain wall based racetrack memory, where we can see that there are two domains. Okay, this domain in which magnetization is in positive x direction, this domain magnetization in the negative x direction, and you know that they are separated by a domain wall, 1 and 0. Okay, so 1 is the magnetization in positive x direction, 0 means the magnetization in the negative x direction. They are separated by a domain wall. When you apply current through this, the interesting part is, when you apply current, you can move these domain walls back and forth. So instead of moving the track, you are moving the data. You can see right now what I'm saying is that instead of moving the whole cube, you are just moving the water inside. You got my point, right? Just to instead of okay, I take water from here to somewhere else, I can fill it in a tank and then I can take it there. That is like a hard disk drive. Whereas I can just put a pipe from here to there and then flow the water. Okay, so that is the second kind of thing. What I'm saying is that there is no physical motion required. The pump doesn't need to move. Only the water within the pump can move. So same thing we are doing. We are applying current and moving these data bits back and forth. But if you want to get a high density, right, what you need to do, you need to create 3D nanowires. So we have tried to create such kind of cylindrical nanowires during my PhD. So I have used this pulse electrodeposition and selective etching technique to create this cylindrical nanowires. I'm not going in deep. I will just explain briefly, just to motivate you the work, not to explain you everything about work. Okay, if you have any doubts, you can always write to me, then we can discuss further. Okay, so what we have used is an anodic alumina template which have small holes, and then we have done electrodeposition at two different potentials. So you can see that we have changed the electrodeposition potential between 1.4 to 1.0, and once the electrodeposition is done, we have released these nanowires and then put it in HNO3. Okay, so you can see that the layers that are deposited at higher potential are nickel rich, which is nickel 95, iron 5. Whereas the layers that are deposited at lower potential, nickel 87, iron 13. So you can see this is an iron rich layer. So when you put them in HNO3, iron rich layers get corroded faster and they become the constructed regions. Okay, so this is exactly what I'm talking. These are the nanowires that we have made during my early PhD, where you can see that this is the non-constructed region, that is the nanowire, and whereas the constructed region. And you can also see that you can call them as magnetic screws. You can see this is a screw. Okay, I must tell you, you should call nanomagnetic screws, because their size you can see is only around 200 to 300 nanometer, the diameter of this nanowires. And you can see that you can even control the length of the each segment. So you can change the length of the constructed region from 75 nanometer to 110 nanometer. But we have to see whether it can store the data, so that whether we can read this data that is stored in this magnetic nanowire. So we have done magnetic force microscopy imaging, which is nothing but it is just like a magnetic tip that will come close to a magnetic tip that comes close to this sample, which is in the magnetic tip size is also I think few nanometers, okay, few atoms. So whether the magnets, let's say that this is also a magnet and the magnetic tip, if they repel, you will get a dark contrast. If they attract, you will get a bright contrast. So it is a tiny magnet. Okay, I have created a nanomagnet, as you can see here. So this is the non-constructed region with before the etching. So once I etch it, you can clearly see there are series of bright and dark contrast showing that I can store data within this nanowires with 1 and 0. So the black can be taken as 1 and white can be taken as 0. Okay. And I have to see whether I can drive this. Yes. What we have done is that we have applied current to this nanowire. You can see that, okay, this is the nanowire where we have made contacts, gold contacts, and we have applied a current pulse. The moment you apply current pulse, you can see the red color. The black color line is showing the positive pulse. So when you apply positive pulse, you can remove the domain wall from there, which means that 1, 0, and when you apply negative pulse, 0 to 1. So you can switch this magnetic, the helical domain wall, the data bit within this nanowire between 1 and 0. However, I must tell you that there is no control over domain wall injection in there. So whenever you are making that device, you should always look into the control. But in this case, there is no control. The moment you create such nanowires, there are already domain walls and domains that exist. To have a controlled injection of this data bits, we have used the in-plane nanostructures. So what I mean to say is in-plane is that this is the in-plane nanostructure. So you can see that I have created using the nanolithography technique, right? We're using electron beam lithography and argon beam ion etching. I have created a nanowire. You can see there is a nanowire, and I have made two contacts with metallic strip lines, so gold strips. Okay, so when this nanowire is saturated in one direction, and I apply current pulse through this current strip, right, what is going to happen? It will create an Oersted field that can switch the magnetization beneath the nanowire. Okay, so whenever the magnetization beneath this nanowire is changing, right, within the nanowire beneath this strip is changing, it will create two domain walls, because whenever it is changing, you will have one domain wall that is formed here, second domain wall that is formed here. And these two domain walls, right, one is called head to head and second one is called tail to tail. It is nothing great. Whenever the two domains are pointing towards each other, that is head to head, they're pointing away from each other, that is tail to tail. That's all. So this head to head domain wall is a positive magnetic charge, can be represented by a positive magnetic charge. And tail to tail domain wall can be represented as a negative magnetic charge. So you can see that I created a positive charge and negative charge. What they will do, they will attract each other. So whenever they attract each other, even though you apply a current pulse, then you will have no switching and you don't have any magnetic data that is injected into the nanowire. So that's what we have seen if you see here that when we apply current pulse even up to 50 nanoseconds, so due to the attraction between the head-to-head and tail-to-tail domain walls, the domain injection into the nanowire is only around 60%. So the probability or the possibility of the domain injection into the nanowire is only around 60%. Okay, but you can never work with a stochastic behavior. Whenever you want to make a device, you always have to work with 100%. Okay, you cannot say that, okay, if you take a calculator, 10 times it tells that, okay, 2 into 3 is 6, but the 11th time it tells that 2 into 3 is 5. You can't agree, because you always have to work with something deterministic. 100% it has to work. But our device, what we have found that it is working only with 60%. So what we have done is to improve this deterministic possibility. Instead of having as you can see here, this metallic strip is within the middle of the nanowire, right? Instead of keeping that in the middle, we have kept it close to the edge of the nanowire. What is going to happen is that the stray field, you know that you can never have a magnetic monopole. You always have a dipole. So this is a magnetic dipole, and it is north pole and it is south pole. So whenever I'm pulsing through this A and A prime, which is the metallic strip, which creates two domain walls. The domain wall that is created at the left edge will be attracted by the north pole or south pole, whatever the pole that is present here. Okay, so the stray field coming from the edge of the nanowire is going to attract one of the domain wall. So there will be no attraction between the two domain walls that are created. So you can get a deterministically injected domain wall. So with that, you can see that I have injected a current pulse and created one domain wall, the black color you can see. So this is 1 and this is 0. Okay, and then I have applied current between A and B to drive this domain wall using the spin transfer torque, which I have explained. And finally, I have injected the current with a opposite polarity so that I create a second domain wall. So you can clearly see this black is the head-to-head domain wall, white is the tail-to-tail domain wall. Why their color is different? The reason is one is positive magnetic charge, second one is negative magnetic charge. So now I have shown you that I can create a data bit where I can have 1, 0, 1. So it's a 3-bit racetrack memory, and then there is no physical motion that is involved. I'm not moving the nano track, but I'm only moving the data that is present within the nano track. Okay, so the current density required is around 10⁻12 ampere per meter square. So let me tell you that whenever you make a device, you will have to quantify few things. That is, what is the power consumption? Second one, what is the speed it can do, and third one is that what is the compactability. So what is the device size, that is whether it can be compacted further or not. And finally, you have to think about a price. Okay, so 4 things please keep in mind whenever you're making a product. You remember all these 4. Okay, now I have shown you that how can I create a non-volatile solid state memory. Okay, now I will talk about the computation, how to do a computation. So this is a conventional CMOS logic where you can see that this is a NAND gate with this CMOS transistors. They are connected in one configuration. If you want a CMOS NOR gate, you need to connect 4 transistors in a different direction. But I was wondering during my PhD whether we can create all logic functionalities in a single device. In using the microelectronic device, you will have to use a different structure for NAND gate operation and different structure for a NOR gate operation. But we wanted to create a single structure to do all the logic functionalities. So for that, what we have used is that just now, as I mentioned, you have 2 types of domain walls. One is head-to-head domain wall, which is a positive charge. Tail-to-tail domain wall is a negative charge. But it has another degree of freedom, that is chirality. So chirality is nothing but you have 2 domains. The domain wall can go in clockwise direction or anti-clockwise direction. You got my point, right? It can rotate in clockwise or anti-clockwise direction. So simply what I'm saying is that the transverse magnetization, just like a spin, it can be up or it can be down. So I wanted to use this chirality to do the logic functionalities. So you can see here that when I injected a domain wall with an up chirality and then drive through this nanowire, right, you can see it is selectively going towards the lower branch. So you can see here from this animation, this is the up chirality domain wall. It is not moving towards the upper branch, but it is only moving towards the lower branch. Okay, and same is true for the opposite, that whenever we inject a down chirality, it will selectively move towards the upper branch. Okay, so we have done experiments.
Sir, small interruption, sir. So the time is 10:54. So I'd
Okay,
like to inform you, sir.
sure, sure.
Yeah.
Thank you, thank you. I'll finish it in 5 minutes. Okay, is it okay, Bhaskar?
Yes, sir. Yes, sir. Okay.
Okay, fine. So I have created this. Okay, I have done this experimentally to prove that you can have up chirality and down chirality domain wall to selectively switch this domain wall within this branch structure. So what I'm saying is here that you can have this domain wall with a chirality can be sorted out. One up chirality can go down and down chirality can go up. So that can be the basis for making the logic operations. So I'll skip all these results. So with that, what we have done is that we have created a domain wall based reconfigurable logic where we have created a single magnetic structure like a branch structure you can see here, and where we can get NAND gate operation, NOR gate operation, and or not copy. All the basic logic operation can be done. And you have a gate over here, which is a metallic strip. By flowing current through this, you can create Oersted field that can select between the different logic gate operations. So we have experimentally proved that. Okay. So we have used the magnetic force microscopy imaging to experimentally prove this logic gate operations. And the best part is that if you can see, when at the upper half ring you have a AND gate operation, whereas at the lower half ring you have a NAND gate operation. So within one logic operation you can get two functionalities. Okay, so when we are flowing current between A to B, you have a NAND gate operation. When we are flowing current between B to A, okay, you have a or NOR gate and OR gate operation. Okay, so this is all about logic operations, and we have also done the wireless communication. And these days, okay, wireless communications are part of our lives, and we have been using it. You know that. Actually, our communication right now is happening through wireless communication. Okay, so how does it help? You can send and receive the data. We need some microwaves. So we have used this spintronics again to create the microwave. So what we have done is that we have used this tri-layer structure in opposite magnetization direction. So when you're flowing electron through this, electrons that are that are getting spin polarized from this ferromagnetic layer can exert the torque on the second ferromagnetic layer to excite the spin torque oscillations. So basically, whenever there is an effective magnetic field, the magnetization precision happens. However, it doesn't happen. It is just like a spin top, but it doesn't work forever. Whenever you are playing with a spin top, it will fall down because of the air friction. Same is true for the magnetization precision. Due to the damping present in the material, the precision damps. Okay. If you apply an external current, then what is going to happen is that you can negate this, you can compensate this spin transfer torque to bring back this steady state oscillation. So this is exactly what we have done. And basically these are the nanoscale RF sources. The dimensions of the device is very small, which can be used in wireless communication application. So basically what we have created is a magnetic tunnel junction with a, you can see around 60 nanometer diameter, where we could get a single mode steady state oscillation by applying current through this magnetic tunnel junction. And what we can show is that we can tune the frequency. By increasing the magnetic field, you can increase the frequency. And by flowing current also, by increasing the current, you can reduce the frequency. So now I'm telling you that you can tune the frequency of these microwave oscillators by two different methods. One is the magnetic field, second one is the current. And we have also demonstrated how to do the signal modulation. You know that you need to do signal modulation. You need to have two waves. One is the carrier wave, second one is the data wave. So the carrier wave is the high frequency wave on which you are going to encode the data. So in this case, you can see that 1 and 0s are encoded as the low frequency and high frequency signals. Fine. So we have shown that experimentally also. I'm just quickly going through. I took a DC current to generate the carrier wave and then applied a modulation current of 0.09 milliampere with a square shape pulse to modulate the data. And the red curve is the external pulse to modulate the signal, and black curve is the output. You can clearly see there is an amplitude modulation following the external pulse. And when we have done the Hilbert transform and got the frequency, and you can clearly see that the frequency of our oscillator is changing according to the external field. So what I'm saying is that you can simultaneously do the frequency shift keying and the amplitude shift keying. And we have shown that we can do that even up to 200 megabit per second. So you can send the data rates, the bit rates are much faster. You can see 200 megabit per second, we can do it using spin torque oscillator. And finally, quickly, I want to go that how to do a cancer treatment with the magnetic materials. So if at all you want to, let's say there is a cancer tumor here. as shown by the red color here, right? So if you take an external drug, right, what is going to happen is it is not only going to affect the cancer tumor, but it is going to affect the whole body. But what we can do is that we can do a targeted drug delivery. You can inject the magnetic nanoparticles here. Okay, as you can see, you can inject it, and using magnetic fields, you can drive these nanoparticles towards the magnetic tumor. Okay, towards the magnetic tumor. And once this comes to the magnetic tumor, you can apply magnetic field, and then you can release the drug, or you can use these nanoparticles to kill the cancer cells close to the tumor. Okay, so this is what is the targeted drug delivery, and this is very much useful not to affect the healthy cells. So for that, what we have done is that we have created these nanoparticles by the same method where, if you remember, I have created the constructions by keeping in HNO3 for smaller time. If I use it for longer time, I can create nanoparticles. You can clearly see this magnetic nanoparticles with various sizes. And okay, and what we have done that you cannot just use these nanoparticles to put it anywhere, because you'll have to find out the cell viability. So we kept this. It's not my work. I must appreciate Dr. Sean Wong from NTU. He has done this work. He has done the cell viability. The cells, you can see even after 48 hours, 90% of the cells are still alive. Then what he has done is that he has used this magnetic field to drive this he has put these nanoparticles with the cancer cells, and then he applied a magnetic field. So when he used a uniform magnetic field, the green color fluorescence here tells that these cells are still alive. But when he used non-uniform magnetic field, this nanoparticles, you can see this. These are the nanoparticles. They start to rupture it, and then you can see the red color shows that the cells are killed. So we can use this magnetic nanoparticles to target a drug delivery and to kill the cancer treatment. So with that, I would like to conclude my talk saying that I have today explained about you mostly, with the time, I explained you how to create a domain-wall memory, what is the importance of spintronics memory and spintronic logic. And I quickly, in 2 minutes, I have explained how to use a microwave oscillator. And finally, I have explained about the cancer cell therapy. And I would like to tell that, okay, there are a lot of challenges and opportunities are present in this spintronics research. So if this talk is only to motivate you to go towards the research in a particular direction. So with that, I would like to thank you all for your kind attention. If you have any questions, please don't hesitate to write me. My email address is mchandrasekhar@msme.iith.ac.in. And thanks a lot for your kind patience. Again, I thank my brother Bhaskar for giving me this opportunity. Over to Bhaskar. Thank you.
So thank you very much, Dr. Chandrasekhar. You have explained a very nice presentation, and it starts from the basics of the magnetism and up to the applications in different areas of like electronics and also the medical and other fields, also allied fields. So it's very informative, and it is exclusively very important for the young researchers, and hope the participants will make the utilize of this one. And before going to close this talk, I would like to ask the participants to have any queries from the question answer side. So Dr. Tiwari sir, over to you, sir. Yeah. Please take any questions from the participants.
Thank you, Bhaskar sir. Namaskar to all of you participants. Please put your queries and questions and doubts in the chat boxes so that we can try to address them.
In between, if anybody willing to talk to our speaker for any few questions, you are welcome. You can unmute your mic and you can raise your question. Thank you.
So thanks for the speaker. I am Professor Bhagavan Narayana.
Namaste, sir.
Are you?
Namaste, sir. How are you?
Okay, fine, sir. Fine.
Yeah, actually, good to see you again. Yeah.
Okay, just I wanted to know one thing. There is a technology that is bubble domain memories like that.
Yes, sir.
So that was actually gadolinium iron garnets or thin films grown on GGG.
Yes, sir.
So this technology that using a laser you can store data, you can retrieve, and you can do all the things what can be done by this spintronics. That was something like 32 years back.
Yes, sir.
IBM has tried to make this technology, but later I don't know what happened. Can you throw some light on that subject?
Sir, actually, yeah, you're right that magnetic bubble memory was about to come. But as you just mentioned, that you need a very high energy to switch between two states, between 1 and 0. Okay, so you have to create some heat, and then that heat has to, then only the magnetic moment can easily go from one direction to other direction. So the power consumption was higher. So by that time, the magnetic bubble memory was about to come. This, as I mentioned, that GMR phenomena, as you know, that Albert Fert and Greenberg has come up. So then the whole paradigm has changed to this to store the data into the hard disk drive, into the magnetic tracks actually.
Mhm.
Yeah. So that is the reason, sir. The power consumption was very high, sir. The to switch between the two states, right? Yeah, you require a lot of power.
Okay,
That
okay.
was the reason.
Now we
This is
have
what I've
better
seen.
technologies that
Yes, sir.
spintronics.
Yes, we have much better technology, sir. Right now, the power
Okay,
consumption is very small. Yeah.
okay, okay.
Yeah.
Actually, some 32 years back, actually, I characterized when they came to our lab. So
Yeah.
later,
Okay.
I don't know actually what happened. That is what I
No, no. By the
wanted
time,
to.
I mean, by the time the magnetic bubble. This is my. I read history, and that's from there. I'm telling you know much better than me. So the hard disk drive, there's a spin dependent
Okay, okay.
scattering. The GMR phenomena has come up, and people, the IBM has started to shift towards hard disk drive. I think you know Stuart Larkin has made this magnetic tunnel junction with a TMR
Right.
phenomena, and he made the read head. So from there,
Hmm.
I think the whole paradigm has changed to hard disk drives.
Right, right.
Yes.
Okay, thank you very much.
Thank you,
It
sir,
is
and
very
I must apologize that I'm eating up your time. I'm sorry for
no,
that.
no. We are happy actually. You have given right from the fundamentals and come to the applications and including the this medical
Hello.
applications also.
Yes, sir.
It
Thank you.
is
Thank you so much, sir.
really an
Dr.
interesting
Chandrasekhar, there is one question.
Yes, sir.
talk.
Thank you, sir. Thank you so much.
Okay, thank you very much.
Thank you, sir. Thank you.
Thank you.
Yeah, please go ahead, sir. Tiwari ji.
Yeah, the question is, how do you manage to measure magnetic phenomena
Mhm.
using oscilloscope and function generator?
That's a good question. Okay, so I think I have explained in the first few slides. Okay, let me put the slides.
Yeah, please elaborate a bit. Na? Actually, the participant said he saw the slides but could not
Okay, I
get
will go
it.
there. I will go there and I will explain.
Okay, thank you.
Yeah, because due to the time constraint, I didn't explain much.
Yeah,
Okay, so
yeah.
so this is what the slide is about. I know. So what to the participant, what we are doing is that we are applying we are applying a current. So there is a magnetic precession is happening, right? So as I mentioned earlier, that whenever the magnetic precession is happening, you will have the change in the resistance. So whenever there is a change in resistance, you will have the electrical voltage that is oscillating. So you are applying basically a DC current, and what you are measuring is an oscillating voltage. The best part is that oscillating voltage, the frequency is in gigahertz range. That's why we call this as microwave oscillators. So now coming to I think you have seen this slide. Yes, in this slide, how we are doing it, right? That's a very good question. So to generate the microwave oscillations, to create this magnetic precession, we apply a DC current. So there is a magnetic precession continuously happening. So the voltage is oscillating. So when the voltage is oscillating, you take this change in the oscillator voltage, that the RF output, you take it and then you send it to the oscilloscope. So in the oscilloscope, you will see that how the magnetization is changing from the change in the voltage. So these are the voltage oscillations that we get it. From there, we can correlate how the magnetization precession is happening. Now, to tell you that what to do with spectrum analyzer, we want to know that at what frequency this oscillatory voltage is occurring. Okay, so that is directly correlated to the magnetic precession. The frequency of the magnetic precession is directly related to the voltage that we are measuring at the RF output. I didn't have enough time, that's why I didn't explain further. But yeah, this is it is. Even though this is a magnetic phenomena, whatever we are measuring is in electrical voltage only. We apply a small bias current, and then we measure the voltage across it. So when you measure the voltage across the tunnel junction, whatever the changes in the resistance can be seen as the change in the voltage. That's all.
Okay.
So
Thank you very much, sir.
thank you, sir. Yeah.
Bhaskar sir, there is no more questions as of now. So if you want, we can give the thanks note. Bhaskar sir.
Sir, do you find any questions in YouTube live chat?
No, YouTube also there is no question.
Okay. So there are no questions. So then let me thank Dr. Chandrasekhar Murupaka for accepting the invitation. And actually, due to some unavoidable situation, yesterday we were a bit worried, and and it's finally, with the God grace, everything is, made it well. So thank you once again for accepting, even in such a situation. My brother and also one of my best friend. So thank you, sir. Thank you. Thank you very much. And your, I think there is a question. There is one thing is rising by someone.
Hello.
Yes.
Can
Yes,
I ask a question?
yeah, please go ahead. Rachna Saini would like to talk to you, sir.
Sure. Please.
Sir,
Yeah.
sir, I want to ask a question about the three para, ferro, and diamagnetic materials.
Yes.
The electron property that is considered in para and ferro, that is its motion, orbital motion, and its spin. But on which basis we are describing the diamagnetic materials? There is a reverse effect, there is a repulsive effect. So can you just explain?
Yeah, I'll try to explain it. Rachna, very good question actually. Yeah, thank you. Okay, so in para and ferromagnetic material, there is an unpaired electron that is giving the magnetic moment. That is fine. But as I mentioned, that diamagnet is completely filled shells. So whenever there are completely filled shells, what is going to happen is that they are going to compensate each other. So let's say one is up, second one is down. So that will give you 0. Okay, fine. So now you see that one is clockwise, second one is anti-clockwise. They are rotating in opposite directions like this. Okay, because you have two spins, right? Two electrons that are rotating in opposite directions like this. When you apply external magnetic field, what is going to happen is that one of these electron is going to speed up. The velocity of the speed of the one of the electron will get higher, and second electron will get lower, because they are in opposite direction.
Which one? It's depend on their spin, the minus half or plus half.
Exactly. You're right. There, plus half. Okay, I'm just, for example, we take plus half gets speed up and minus half gets slower down. So when one is speeding up and second one is slowing down, what is going to happen? You get a current there, right?
Yes.
Because earlier both currents are same, because both are rotating with the same speed. Now one is going with a high speed, second one is going to lower speed. There will be an effective. Exactly. So there is an effective current that is present in there. That effective current will give you the magnetic field that is opposing the parent, like Lenz's law, that is going to opposite the external magnetic field. So that's all actually.
Okay. Thank you so much, sir.
Thank you so much, Rachna. Yeah, I'm happy that you people could get what I'm saying actually. And thank you. Yeah.
It's really a nice lecture, sir. It's really a nice.
Thank you, Rachna. Thank you so much.
Okay, so thank you all the participants. And for your queries. And now I'd like to close the session. So close this talk. So before that, I would like to thank our speaker for accepting the invitation, and it is very excellent talk, and it is very useful to the students of RGKT, and also to the outside people of research scholars, and also many PG students are also part of this one. And whoever is working on this area, definitely, as like you said, if they need, will provide the email ID to them, and whenever there is any interaction, let them contact. And
sure.
With that, I would like to thank the speaker. So thank you very much, and soon maybe even we can have some more webinars based on your schedule. So in future also. So thank you very much for your acceptance, sir.
Thank you so much. Yeah. Now I think the next talk is from Bhavan Narayana sir, right?
No, sir. Next talk is from Ravi Kumar
Okay, Ravi
Pujala.
Kumar
He is
Pujala.
from
Okay, I said
from
Tirupati. I know.
yes, I sir Tirupati. Yes, yes,
Okay. I'm looking forward for it. Okay, so
yes,
I'll
yes,
close my video. Thank you everyone for your kind attention. So I'll be online, but I'll be listening to the talk. Thank you so much.
yes. Okay, thank you, sir. Thank you. So the next session starts. So Ravi Kumar, sir.
Hello, good morning.
Yeah. Okay. Okay. Thank you very much. So yes. Good morning, sir. So Karthik, sir.
Yes, sir. Yes, sir.
Yeah. You please start the session as per like our schedule.
Yes. Good morning, one and all. I am delighted to welcome you for the Day 3 Talk 2 of the International Webinar Series on synthesis and characterization of nanomaterials and their novel applications. The talk is going to present by Dr. Ravi Kumar Pujala, Assistant Professor, Department of Physics, ISER, Tirupati, on the topic Sculpting Silica Colloids at Nanoscale and their applications. Now I request Mr. Bhaskar sir to introduce the speaker.
Okay, so thank you, Dr. Karthik. So now I would like to introduce our next speaker, Dr. Ravikumar Pujala. He is an assistant professor in Department of Physics at Indian Institute of Science, Education and Research, ISER Tirupati. He obtained his BSc from AP Residential Degree, Nagarjuna Sagar, and he did his Masters Physics at Jawaharlal Nehru University, JNU Delhi, and also he did his PhD at JNU Delhi in 2014. During his PhD, he has discovered formation a new state of matter colloid equilibrium gel using naturally occurring nanoclays, and he then moved to Greece and he did his postdoc at University of Crete, and he did another postdoc at Utrecht University, Netherlands, and he was awarded DST Inspire Faculty in 2017-18 by the Government of India, and he contributed his research and teaching at the University of Hyderabad. He is now the assistant professor at ISER Tirupati, and he received many awards like visiting professor awards, CNRS France and DST Inspire Faculty Awards, and also Marie Curie Award, and he received a Best International Award in 2014, and he has more than 20 research articles and 2 books of international level in reputed journals. So with this few introduction, I would like to hand over the session to our beloved speaker, Dr. Ravikumar Pujala. Over to you, sir.
Thank you, Bhaskar, for the kind introduction. I'm going to share the slides. Please let me know if it works. May I know if it is visible?
Yes, sir. The presentation is available.
Okay.
Yes, sir. It is visible.
Hello all, good morning. So today I'm going to talk about sculpting silica colloids at nanoscale and their applications. I'm working as an assistant professor at ISER Tirupati. So this is the plan of my talk. I'll first introduce why these silica structures are important and what we, why do we use in daily life and what kind of application that we get. And then I'll talk about the synthesis part. How do we, come up with the different strategies to synthesize anisotropic nanostructures. And then I'll talk, focus on a little bit more on liquid crystal colloids, and then their self-assembly strategies. And then I'll talk about applications, then and there. Before going to the main presentation, I would like to introduce our institute. Indian Institute of Science, Education and Research, Tirupati. Our motto is creating infinite possibilities. So this is located in Tirupati, the southern part of India, where you can see this mark. So I hope many of you know this Tirumala temple. It's a worldwide, world famous temple. Our vision is to be a basic science and technology-driven institution of excellence, wherein science education seemingly integrates with the state-of-art research and skill development. Our goals are to train quality scientific manpower for India. We also to research-led teaching institute, providing early exposure to research, and we encourage students to work in interdisciplinary areas to integrate science with technology, industry, and society, and also development of lifelong competency skill in students. And we have three kinds of programs. We offer three programs. One is BSMS dual degree program, which is for 5 years, and other one is integrated PhD or PhD programs, which is integrated PhD is after post BSc, MS or MSc, and PhD is of course after MSc. And we have another program which is postdoctoral. So if you want to know more about our institute, if you are interested, you can have a look at our website, www.isotirupati.ac.in. You will get more updates, and you will also see the profiles of our faculty and what are our current interests, how we are excelling in these difficult times as well. Now, I mostly work on soft and active matter. I'll introduce briefly later on, but my focus is on soft and active matter. We have a number of scientists working in the same area in our institute itself. Dr. Dilip Mampalil, he is working in microfluidics. Dr. Tapan Chandra, he is working on active matter. He is simulating active matter systems. And I am an experimentalist working in soft and active matter. We three are from physics department, and Jatish and Rakesh are from chemistry department. So we work in different fields, but we work in this vast interdisciplinary field of soft and active matter. So these are my research areas for group, soft and active matter group. First, we focus on fabrication of nanostructures, either isotropic, anisotropic, and more complex structures such as genus particles, patchy particles. And also, we self-assemble them. We use different strategies to make useful structures that we see in daily life. Some of them are colloidal gels, glasses, or equilibrium gels, which I explored in my PhD. And we use certain kind of external fields to assemble them even. So you can see a nice alignment of anisotropic structures. These are nanorods, which I'll talk about these nanorods today, nanosilica rods. And also, we can assemble them in different media. We can assemble in water, and also in a liquid crystal medium. And we can, self-assemble them and make very fascinating structures. And the other one is out of equilibrium, which are active systems. Sorry. So you can see here, so we are interested in mimicking the living matter. So we come up with different strategies to mimic, let us say, the natural examples such as bacteria or some other organisms that self-propel themselves or swim and make large structures out of equilibrium structures. So these are my area of interest. I'm mostly going to talk about today on the fabrication. I'll spend more time on fabrication and self-assemble strategies. And I'll come at the end, I'll come to this part out of equilibrium systems. Yes. So let me just introduce what is soft condensed matter. It refers to a condensed matter that exhibit characteristics of both solids and liquids. So the phrase soft matter, which was used by Pierre Duchesne as a title of his Nobel Prize acceptance speech. Soft matter, it can flow like liquids. So where we can measure the viscosity. Soft matter, it can bear stress, which is it can have an elastic deformation. So soft matter behaves as a viscoelastic material, which means viscous and elastic. Some of the examples that we see in daily life are rubbers, gels, pastes, creams, paints, soaps, liquid crystals, proteins, and cells. So without soft matter, we cannot live. Once we get up, we use, we have to use soft matter. For brushing, when we get up, we use the toothpaste, which is a soft material. We can, deform. Inside it is a solid. When you squeeze it, it becomes a liquid, and when it comes out of the, and then sits on the brush, it becomes a solid again. So these kind of, what kind of interactions govern these systems, and how to characterize these systems is very interesting, and is very actively pursuing field, you can say. So even in soft matter is an interdisciplinary domain, bridging chemistry, physics, biology, and material science and engineering. You can see a variety of fields, interdisciplinary fields that emerging out of soft matter. So mostly I focus one kind of soft matter, one class of soft matter, which is colloids. I hope the participants are aware of a colloid. A colloid is a submicron particle, one phase which is dispersed in a continuous phase. We have a dispersed phase and a continuous phase. Based on the dispersed phase and continuous phase and their combination, we can obtain different materials. So here, if it is a liquid or solid in gas, this is aerosol. So nowadays we mostly worried about this aerosol because of corona or COVID-19 virus. So if a dispersed phase is gas and continuous phase is liquid or solid, we can form foams, which are shaving foams, polyurethane foams. So and then liquid emulsions. So all these examples we see in daily life, and what kind of interactions between govern these kind of structures. So that is the area of my interest, to understand the basic or fundamental understanding of interactions between the species that we use in daily life. So colloids can be tuned. So we can also see under a microscope. With a very simple microscope, we can see them, and we can see what they are doing, how they are behaving. So that is why I got interested in such systems, and worked on that. So even in the colloids, I'm going to talk about silica nanoparticles. Why silica is important? So we can use them as an additive for the manufacture of rubber and plastics. We use them as a strengthening filler for concrete and other construction composites, as a stable, non-toxic platform for biomedical applications such as drug delivery and theranostics. So there are a lot of applications we can talk about, and also we call colloidal atoms. Atoms cannot be tuned anyway. So, but here, even to understand some of the phenomena that is happening at very small length scales, can be understood using colloidal science. So today I'm going to talk about mostly, so far, spherical colloids, spherical silica colloids or spherical colloids are well understood, and their phase behavior. How do what happens when we have a dispersed medium, let us say water, and we put a bunch of proteins or spherically shaped particles. So how do they behave? What happens at different concentrations? How do they behave at different temperatures. So all these things are well understood, but nowadays the focus is shifting towards the anisotropic particles, which I'm going to talk about today. So here we start with a very simple strategy. It's a single port synthesis, silica rods, silica nanorods. Here we have an emulsion where pentanol PVP is a continuous phase, and ethanol, ammonia, water is and sodium citrate. So we have droplets of water, droplet consisting of ethanol, ammonia, water, sodium citrate dispersed in continuous medium, which is PVP and pentanol. Now we supply reactants, we supply precursors so that they can react and form and grow nanostructures in anisotropic directions. Because of the supply of reactants in anisotropic direction, they grow along one directions. So these are one-dimensional rods. So this is the focus of my research. I'm mostly going to talk about these particles. So these are this is very easy synthesis and single port synthesis. We can do even at home also. You can synthesize them at home, these structures. So this is how they look like. Once we form these nano rods, they look like this. So we can see them through under a TEM, transmission electron microscope, or scaling electron microscope. We can do a lot of interesting stuff. We can self-assemble them and form some nematic liquid crystalline structures or smectic structures. We can even see them under a confocal microscope by coating with a fluorescent dye. So even during the synthesis itself, we can add the dye and then let the reaction continue. Or else we can also do the confocal fluorescent dye after the synthesis also, and then coat again with another layer of silica so that it doesn't bleach out. And so it's just there are many more conditions to tune in this case. So I just mentioned here only ethanol at room temperature is what droplets in continuous medium at room temperature. But what happens at different temperatures? So the controlling parameters are pH, time, and also silica precursors, and pH of the solution and temperature mainly. So we'll see what these parameters could contribute to the final product. Yeah. So based on, as I told, we can check rods by tuning the hydrolysis and condensation of the silica precursors. Here we use silica precursors, TEOS, tetraethyl orthosilicate, and tetramethyl orthosilicate. Methyl orthosilicate is more reactive than ethyl orthosilicate. So here, just have a look at on the left panel. So here, during the reaction itself, we can tune and we can add more water, or we can hydrolyze silica precursor. So when we pre-hydrolyze the silica precursor in the beginning itself, or we add the silica pre-hydrolyzed TEOS in the beginning itself, we get very interesting steps which are matchstick like colloids, matchstick particles. So if we keep on adding more pre-hydrolyzed TEOS, so we somehow go and end up with hollow spheres. So this is a SEM picture where we can see the FIB-SEM, where we can see the inner is hollow. So because of the reaction, the condensation is taking place from the outside of our droplet. So this is a silica and oxygen that you can see EDX measurements. So what more can be done? This is the pre-hydrolyzed TEOS was added before the reaction, but when we add them some in the middle of the reaction, we see a different structure. So here when we add the pre-hydrolyzed layers, we get mastic particles, or based on the concentration of pre-hydrolyzed layers, we get different mastic particles or hollow structures. But when we add these pre-hydrolyzed layers in the middle of the reaction, or sometime in the reaction at some point of time, we get these bent structures, bent rods. So we can quantify them, their angle, and what concentration we get, what angle. So this is all controllable reaction and easy. And what else can be done during the synthesis itself? We can use some catalysts. Here we use benzoic acid, where we can grow more complex structures during the reaction itself. So this is about the pre-hydrolyzed layers. When we use TMOS in the reaction itself, in the droplet, when we mix with the TEOS and TMOS, and then we add TMOS instead of pre-hydrolyzed layers, we get different structures like hockey, hockey sticks kind of stuff, dumbbells, depending on the addition of time of addition TMOS during the reaction itself. So we can also form different segments. So the growth can be also done in segments. We can tune the reaction at any point of time so that we can get desired structures. And we can even we studied this reaction, what is happening internally. We used transmission electron microscope and cryo-TEM imaging. So we can actually see what is happening, what kind of shape it has, and what is the internal structure. So when we add TMOS, it generates a hollow structure here, and then due to some viscoelastic behavior of the droplets, they squeeze them, they are squeezed, and then it tries to bend somehow, and the addition of again TEOS will result in bent-like structures, bent-like rods. So bent silica rods are more interesting because in the molecular liquid crystals we see molecules which are not visible. Here we can form such, we can mimic such liquid crystalline structures using bent silica rods. Here instead of TMOS or pre-hydrolyzed layers, one can use heating or pH during the reaction, and also form a controllable bent angle during the reaction itself. So, and then when we self-assemble, then when we add more and more particles to the suspension, it forms an entropy-driven transition, and then make very interesting structures which are not absorbed, which are absorbed in the liquid crystal medium itself, in the molecular liquid crystals. So you can see when we place them under a polarizing microscope, a polarizer which blocks certain kind of polarizing, and then allows certain other kinds of polarizations entering through it. So we can see their orientation, even what kind of arrangements that are there, in the system. So these BSRs, bent silica rods, could serve as a new visual model for understanding the phase behavior of banana-shaped liquid crystals. So we can mimic the phase behavior of banana-shaped liquid crystals, and they may find applications in conventional photonic fabricating structural materials. So even more interesting, by long-range positional order, which is frozen in disorder, but short-range orientational is which is a dynamic one. So here one can tune this interaction between the particles, or by tuning the solvent properties, one can obtain a plastic crystal, and this can be easily tunable by the external fields. As I mentioned earlier, we have used electric field, magnetic field, or gravitational field to align such particles. Here, one such example is plastic crystal transforming, and when we apply electric field, it transforms to a fully crystalline state. And you look at the concentration or the volume fraction, which is very, very low, 0.006. So, but in spherical colloids, it's entirely different. In anisotropic nanorods, they could come up with a fully crystalline structure at very, very low concentration. That means few particles to make these crystalline structures. So even a plastic disordered glass can be transformed to a fully crystalline state by applying an electric field. So there are many, these kind of new phases provide insight into the role of rotations in the phase behavior and could be useful for photonic applications. So far I talked about the synthesis and what kind of structures it gives when we self-assemble them. Now, even more interesting, this is a recently developed field, liquid crystalline liquid crystal colloids. So some of the most exciting recent developments in both of the soft matter fields emerge at the interface, liquid crystals and colloids. So it is when we work at the interface of these things, which is nowadays fast growing research area of liquid crystalline colloids. So major scale self-assembly in such systems may lead to artificial materials and to structures with emergent physical behavior arising from patterns of molecular order and nano or microparticles. So this is we have now, if you have a robust control over their rotations and then orientations, we can come up with artificial materials or the intelligent materials. So liquid crystal colloids show exceptional promise for new discovery that may impinge on composite material fabrication, low dimensional topology, photonic crystals as well. So we have used these nanostructures, silicon nanorods, and then place them in an anisotropic medium, which is liquid crystal displays that we see here. So we have a thin layer of liquid crystalline material, and then disperse these nanorods in such a thin film, and we see a lot of defects that is happening when we just disperse a nanorod in thin film. And by carefully tuning their orientations using a trap, which is an optical tweezer, we can trap a colloidal particle and bring them together, place the way we want, which is otherwise not possible in an isotropic medium. So this is a polarized imaging, and this is a lambda plate. So we can see linear polymer chain kind of stuff here, and also not only that, we can even make more architectures, matchsticks like shape formed by a dipolar spherical colloid of diameter 1.1 and a nanorod. So we can even form a snake charmer's flute kind of stuff. Even here we can see. So this is only possible to do these elastic interactions between the particles and the defects that they are forming around the particle. And even more complicated structures we can assume, and we did so. So this is if we consider only rods, we call them we call them linear polymer chains, or AAAs, homopolymers, or else we can also put co-assembled structures of microspheres or nanorods, microrods. We even make very long range order structures, such as I showed here. So we can orient them. We can place a nanorod and a sphere, nanorod sphere, or else nanorod, microrod, nanorod. So this ABAB, or even co-assembles of rods, nano rod, micro rod, nano rod, or sphere. And even more interestingly, we could able to make these centipede structures, which is observed in nature. So this is the previously I spoke about one-dimensional structures. Here we also made a two-dimensional binary colloids. This is a 2D crystal of binary colloids where we use nano rods and spheres, microspheres, and then form a 2D array of these spaces, 2D crystal of binary colloids, which is this is a POM image, and this is with the lambda plate, and this is without. This is what we see under microscope. But when we look through a polarizer, we get a different picture. So we can see what kind of defects that are there around the particle. So this is about nano rods and micro rods, and we also made structures with binary colloids or co-assemblies of spheres and rods. So even we can come up with more applications. Here cubes, which is these are slightly rounded in shape, and we can coat a silica layer of around 60 to 80 nanometers in thickness, and based on the conditions that we use, we can grow the rods even on this particle itself. Here, when we play with water and ammonia concentrations, we can grow rods even on these kind of on these cubes, hematite cubes, or any other material. It is possible. Here, so we grew a layer of silica on these particles, and then again we did the same as we did with the rods in liquid crystals, and we can even see the orientation, orientation of 3D orientation of microscope, microcubes with induced defects. So we can self-assemble them even with different structures, which is we just recently published this one. So here these are all laser tweezer assisted assemblies of microcubes with the bent chains, branches. We can see branches, 2D crystals, kings, and then cross loop structures. So all these are possible with liquid crystal colloids, and we can come up with even more complicated structures and with more complicated colloids. So this is what I have on liquid crystalline stuff, and then what more can be done using these structures that I have synthesized, that we synthesize nano rods. Sorry, is it fine? Okay. So yeah, so we move on, and then we have gone to a different field. So far we tried to self-assemble them in isotropic environment and then anisotropic liquid crystalline medium. Here we assisted them by using a trap or an optical tweezer, a laser tweezer. We move them around and put them together to form these structures. Now what happens, we can even tune these particles even in isotropic medium, even in water. So these structures can be these colloids can make motions with some kind of chemical treatment or chemical reactions that are happening around a particle. We can even make structures or the swimmers which are naturally which we can mimic the natural phenomena, such as bacterial stuff or swam of fish. So we can I'm going to show how we use these structures that we made and use them to self-propel and mimic the active matter. So which I'm going to a different field, slightly away from equilibrium to a non-equilibrium stuff. So these are active matter system. What is an active soft matter or active matter? So it's a novel area of research at the interface between biology mathematics, soft matter, physics that is being developed to understand physics behind the non-equilibrium systems such as bacterial colonies, tissue formation, cancer growth. And active matter has recently witnessed the emergence of promising new direction. So which is a design. First is to design and then use them for the construction of biomimetic active material, which are essentially ensamples of artificial active particles. So you can see some of the examples of active matter here. So bacterial colonies or Starling flocks at twilight. And now, how can we make our particles, our systems active? So what are active particles by then? So there are two classes of colloidal suspensions, which I told earlier. Which one is equilibrium, and another is active, which is maintained out of equilibrium dynamics by external fields such as magnetic field, light, chemical reactions, or hydrodynamic shear flow. And an active particle is a particle which can convert energy into a work in order to self-propel or make small motions, and which produces enhanced motion within the fluid environment. So the responsible mechanisms I'll show in a minute. So here I'm just mentioning interfacial phoretic effects such as electrophoresis, thermophoresis, which I'll show briefly in the next slide. So why it is important, why active particles are important, is because sensitive particles that mimic the self-propulsion of living mechanism has been at the center of most exciting lines of research in the present soft matter. So how do we make motions of these colloids or the particles? So one way of doing it is using the diffusophoresis mechanism, which is spontaneous motion of dispersed particles in a fluid induced by diffusion gradients, which are called chemical gradients or concentration gradients of molecular substances that are dissolved in the fluid. So when we make chemical, when we change the chemical nature of a particle, one side is having a different chemistry, another side have a different chemistry, and based on the reaction that is happening with the solvent molecules, particles in molecules in the solvent and the surface, or else we can also get a different mechanism. So we have to maintain here chemical gradient or the diffusion gradient so that they can swim in a particular direction. Another way of doing is thermophoresis. Particle motion is induced by thermal gradients. So if we maintain chemical gradients, temperature around a particle, they also move in a particular direction. Another is the electrophoresis, motion of particles relative to the fluid and due to the electric field imbalance. So I'll show one of these examples, one after another, and I'll come up with what applications we can derive using our particles. So there are different strategies, as I told earlier. There are strategies for fabrication of active colloids. There are special type of particles. These are genus particles whose surfaces have distinct physical properties. Here, these are genus particles. We can make them half one substance, another half with a different material. So this is this comes from a Roman god. So let me just I have a few more slides and then I'll conclude. So here, so based on the mechanism, diffusophoresis, one of the mechanisms. So people, Balanci, they came up with a very innovative idea of propelling the particles. So they what they did, they inserted a photocatalytic material inside a silica particle or a colloid, and then when they shine the light, so based on the interactions between light, this photocatalytic material and the light, and in presence of a fuel, we need a fuel which is here H2O2. So it decomposes the H2O2 and maintains chemical gradients around the particle. So here, gradient osmotic, we can see the solvent flows around this particle and the gradient is maintained and it moves in a particular direction. So when they shine the light, the particle they move, and when we switch off the light, so they disperse. So in such a way, one can form these active living crystals or active living crystals from active particles. So this is from a spherical particle. One more very nice paper by Granick group, which is reconfiguring active particles by electrostatic imbalance. So one of the strategies is maintaining the electrostatic imbalance. One can form isotropic just particles and then chains, even the swarming behavior, clusters. So all these things can be maintained just by simply varying the frequency of the electric field. And the other one, so there are more interesting fields. I'm not going to going into details. There are many more applications, but I'll simply list out one application. Here, this is a genus particle. So one can use such a self-phoretic genus microswimmers to trap these particles or to transport this cargo. So as you can see here, so one genus particle, it captures another particle, another magnetic particle or paramagnetic particle, and it transports in a particular direction. So this transport can also be done by single or double genus configurations. So this is a very exciting field. We can even use them for the direct delivery applications. So so this is what we synthesized group in previous group. So here instead of using spheres making janus, here we made janus rods, which is platinum, coating platinum at 1/2 or a hemisphere, half of the part, and then other half is silica. So when we inject the fuel, so this is when we inject the fuel, they self-propel in a particular direction. Here, they are propelling sideways. So in such a way, just due to this behavior, motility, it induces a phase separation between dense living clusters and the dilute gas. So here, they have not seen a qualitative difference between this aspect ratio, but they all form this kind of motility in this phase separation or the living crystals or living clusters. So this is another way we are working on light activated propulsion by placing a photocatalytic material at another end of the rod. Instead of placing in a spherical, we can also do it by placing it one end of the rod during the synthesis itself, and then we can put them in fuel and make them move. So these kind of synthetic motors, which can move cargo in a well-controlled way through a liquid environment, are of significant interest for the applications such as targeted drug delivery, biosensing, and shuttle transport of living cells. So this is what we can make. We can insert a photocatalytic material at one end, and I'm not going to show how they move. If you're interested, you can write to me as well. I'll show you their motions as well. So another way, this is going to be my last slide, where we have cubes by carefully controlling the chemical nature of one side of the cube. We made them self-propel, and then we can see a role of anisotropy on the same direction using these cubes. At very low concentrations, they just move. You can see the active motions of these cubes. But at very higher concentrations, we can see living chains, polymer-like chains, monopolymer or chains or branch chains that we can see. So in summary, so silica structures can be tunable by various parameters, and silica rods, when we self-assemble them, we can use them for different applications. One such application in photonic applications. Mimicking the living matter is possible with the current available techniques or theoretical models, and we are complex details of living matter is being investigation with the help of active clients. So nowadays autonomous applications are realized in some systems as well. So with this, I would like to acknowledge my collaborators, Professor H. Bodhar from JNU, and Alphonse van Bladeren from Utrecht University, Professor Arnaut from Utrecht University, and Professor George Petikidis from Greece, Dominic from Edinburgh, UK, and Professor Sujit Dara from University of Hyderabad, and Ramakrishna Kotni and Fabian from Utrecht University, Netherlands. And then my funding agencies, just Inspire Faculty, ISA Tirupati funding, and also other funding such as Microsoft Greece and Advanced ERC, the Netherlands. Thank you for your attention. I'm happy to answer if you have any questions.
Thank you, sir. Thank you for a wonderful session. So, Dr. Deepika, madam. Dr. Deepika is present. Okay, so some of the participants are unmuted their mic. I request Dilip Kumar Mishra to unmute. Thank you, sir. Thank you for your wonderful session. It is actually it's a fundamental research. Like the ISA Tirupati is very. It's like as you said, it's a world-class, famous place, and many of the people are visiting to Tirupati, and this ISA will make a better product to the country and also to the world, and we are happy for that. People are earlier also there is one speaker from your side, Tapan Chandra Adhyapak, like what you said, he is in our group and in your group, and he has presented a session in National Science Day during on 27 and 28 February in the institution. So like
He's also watching now.
yes. Okay. Thank you, sir. So now it is open for question and answer session. So any questions from the participants? Later we'll continue this one. Any questions from participants, please?
Hello, good morning, sir.
Good morning.
Yes. Yeah, Vishwanathan, Balga Vishwanathan, please go ahead.
Good morning, sir. It's a nice presentation.
Okay, yeah, Dilip, fine.
So I have a small doubt, sir, in that synthesis of the silica rods. So you are using the combination of ammonia and other chemicals. So in that process, which chemical acts as a structure directing agent, sir?
Sorry, can you repeat that?
Structure directing agent. So which chemical can act as a structure directing agent?
Structure directing agent.
Yeah.
So here, if you see here.
Hello.
So this is can you hear me? Hello.
Yes, sir, it is audible.
Okay. So here, this droplet consists of ethanol, ammonia, water, and sodium citrate. So here,
Yes,
sodium citrate it acts as a stabilizing agent for the droplet, and ammonia acts as a catalyst in this case.
Okay,
and,
sir. Means that ammonia will certainly monitoring the structure, or maybe the
structure, but it has a different nature. So once the reaction, let's say the precursor is added at this point, so it starts to condense at this point of on the droplet, and due to the supply of these reactants from this direction, So it's continued to grow, but this mechanism is still not clear for us. We are
Okay, sir. Okay, sir.
with a better understanding on this. Still,
Okay, sir.
I think that it's
Sir,
yeah, please.
it's like in a hydrothermal process, or maybe you can say that you are condensing and heating. So this is in a hydrothermal method, or some other
No,
method we can.
it's a room temperature synthesis. So
Room temperature.
yeah, it happens at room temperature. But if you want to control the reaction, we can use some kind of boilers. We can place them. We have to keep them at constant temperature. Or
Okay,
if
sir.
you
Okay,
want to
sir.
get a different structure, such as bent rods, so we have to
Okay, sir.
maintain different temperature, but it should not vary much. So the
Oh,
fluctuation should be very little. Otherwise, you'll
okay,
get a
sir.
lot of non
Okay, sir.
very ugly looking structures.
Okay, sir. Thank you very much, sir.
Yeah.
So any more questions from the participants?
Yes, please. I am Professor Bhagavan Narayana. Just speaker, sir.
Yeah,
Sir, go ahead, sir. You please ask a question.
I can hear. Yeah.
Sir, I have a question. Sir,
Yes, please.
Close to the social technique or
I have a question.
any other? Pardon? Hello. Are
Yeah,
you?
yeah, please, sir.
Am I audible for you?
Sir, please repeat the question. In between, some other participant has asked. Can you repeat the question, sir, please?
Actually, just it is only query. This method of growing the silicon rods, is it a sol gel method or something else?
Yeah, it is salt gel.
Okay. And your ammonia is acting as a capping layer for that?
No, it acts as a catalyst for the condensation, the hydrolysis and condensation.
Okay. Thank you very much. And thanks for a nice talk. Okay.
Thank you.
Hello.
Yes.
Sir, I am Dilip Kumar Mishra from Ravenshaw University, Cuttack. Hello.
Yes.
Yeah, sir, I am already working upon the silver nanorods. So I have a little bit experience that when I am synthesizing the silver nanowires, it is the problem of agglomeration. So similar problems can be happen in silicon nanorods. Another
No,
question.
it doesn't happen because
Yes, sir,
we
yes.
stabilize droplets properly, so that the interaction between the droplet coalescence it may happen if you wait long enough. So these droplets can coalesce and form a bigger droplet, and the diameter of the rod may be different. But they are stable at least for a certain time until we make a reaction process.
Yeah. After centrifusion for your materials, how you are preserving? I am just keeping in methanol. In which media you are preserving for long duration for next application process?
We use ethanol, basically. We store in ethanol.
Ethanol, sir?
Ethanol. Ethyl alcohol.
Sir, when we are preparing the slides for FESM or TM, like we can drop past directly ethanol material or anything?
The ethanol medium itself, we can quickly dry them.
Yes, sir. Can you help me the experimental process of preparation by PPT? Share me.
Yeah. You can write to me. I'll try to send the information.
Yes, sir. Sir, I am giving my address in chat box. Please send me. Yes, sir.
Yeah, that case.
Thank you.
Dilip Kumar, actually, you can do another one. You just search. Anyway, SAR melody is available in the first slide itself. You can refer YouTube it is available. If not, you can check in our website. ISER website also is email ID is available, so that you can contact. Hope it is
Yes,
fine.
sir. Lot of thanks.
Sure. Any more questions from the participants? Okay, if there is no question from the participants, actually there is a question from my side. Sir, actually, sir, I'm happy for that since you have worked in different areas of this colloids. Actually, this laser trapping you have mentioned, no, sir. So this even I myself did my MTech project on the this laser. This optical tweezers, trapping and manipulation of micro nanoparticles and biological cells. So actually, my question is general. Recently, in when ISER Tirupati and IIT Tirupati also started this canast, right? So,
Yes. Yeah.
so actually, it is related to all kind of like atomic and also optical kind of this areas is there. So my general question is that how this optical tweezers or the trapping of the materials by the laser will lead to the quantum technology. Can you throw any light on it? Quantum technology. Yes, yes.
I'm not much aware of this technology, but
actually, sir, now the next progress in this area is this quantum technology. For that, even this optical, this trapping is also is going to take a lead. Even I have attended some of the seminars, webinars like this, where some of the people are shown. There are certain areas. One among the this quantum technology is this laser trapping of atoms and molecules. So I'd like to know if we have any help, if you know any idea on it.
I have gone down to molecular levels or in quantum dot. So
Yes, yes.
mostly we try to confine ourselves in higher than 1 micron. And then
Okay, yes, yes.
Tracking gets better. It's better in such systems.
Okay, okay.
So since we use the microscope, we have to see at which place which particles are there. So we have even to look at the particles. So even we need a good high resolution microscope.
Yes, yes.
So,
more than and that, sir, another point. Your the research. You recently have published a paper in this trapping of these colloids only.
Yeah.
So, the facility is available in ISER Tirupati, or you have worked somewhere else?
So I worked in University of Hyderabad.
Okay. Yes, yes.
Still,
yeah.
But we use of our own instrument.